call this equation B. Okay. So therefore, equation B becomes y as a function of x, which is equal to C1 sine, oh, hold on, not Ci, okay. C1 sine small px plus by C2 cos px. So this is our equation C. Now, from here, we know that P, right? Note. So from here, what I'm going to do is I'm going to bring in our diagram, this diagram over here, so you can see the boundary condition clearly. Okay. So we're going to look at this diagram now. Right? We're going to look at the, so what we have to do now is we have to determine what is our C1 and C2, okay? So I'd like to get you to recall that note that small p is equal to square root big P over EI. And we know the big P is the axial load. Okay. So big P, you ask me, Eugene, where's big P in that diagram? Okay. So big P is over here. Okay, big P is over there. So we are going to introduce, okay, we're going to substitute the boundary conditions we're going to substitute the boundary conditions into equation C. Okay, so we're going to substitute boundary condition number 1, which is when x is equal to 0, right? Y is equal to 0 into equation C. Okay, so we are basically using this equation or this boundary condition over here. Okay, so from here we can substitute into equation C. So we know that this is 0 is equal to C1 sine P multiplied by 0 sine of P multiplied by 0 plus by C2 cos P multiplied by 0. So from here, sine of 0, this thing is equal to 0. Cos of 0, this is equal to 1. So therefore, we know that C2 is equal to 0. Okay. So now we are left with the expression. We know that C2 is equal to 0. So y as a function of x now. So this is equal to C1 sine px. And this is our equation B. Okay, that is equal. So the next thing that we're going to do is we're going to substitute boundary condition number 2, where we are going to use this expression over here, or this relationship over here. Okay, this relationship over here. And I'm not going to call it L naught, I'm going to call it L, where x is equal to L. Right? Y is equal to 0 into equation okay, into equation D. So from here, we know that y as a function of L. So this is equal to C1 sine EL. Okay. So we also know that y at a distance L is equal to what? 0. Okay. So the next thing that we have to consider now, in what condition? Okay, in what condition okay, where C1 sine PL is equal to 0 is true, right? So the condition is where PL is equal to N multiplied by pi, right? Where N is it can be 1, N can be 2, N can be 3, and N can be what? 4. Okay. So now if PL is equal to N pi, so we can write that sine, okay, we can write that PL, right? We can write that PL is equal to N pi, right? Because when PL is equal to N multiplied by pi, this expression will always be true, right? Because pi, sine of pi is equal to 0, sine of 2 pi is equal to 0, sine of 3 pi is equal to 0. So from here, we have developed a relationship where we call PL is equal to NX, okay, or N multiplied by pi. So from here, P is equal to N pi over L. Okay. So this second boundary condition still satisfies when y is at a certain distance L, the deflection is equal to 0, which is boundary condition number 2. Okay. But from this condition, we found a relationship where small p is small p is equal to N multiplied by pi over L. Okay. So from here, this is our this is our equation E. Okay. So we also know that small p, note that small p is equal to square root big P over EI. Okay. So we're going to substitute P equal to small p is equal to square root of big P over EI into equation E. Okay. So from here, we know that square root, now this is capital P, yeah? P over EI is equal to N pi squared over L squared. Okay. So we have P over EI is equal to, oh, no squared yet, okay? So this will be equal to N squared pi squared over L squared, okay? So if we were to rearrange this, we have P is equal to N squared pi squared EI over L squared. Okay? And then we are going to call this P critical is equal to bracket N squared pi squared over L squared multiplied by EI. So note that the critical load or critical axial load or PCR, okay, is the critical axial load, okay, where buckling will occur. okay, where buckling will occur. So we can also express this as stress critical, which is equal to P critical divided by area. So this will be equal to N squared pi squared over L squared EI over A. Okay. So we are now going to focus on mode 1 buckling. Okay. So in or N will define the modes of buckling. Okay. So let me explain what is going on down here. Okay. When N is equal to 1, right, which is what we call mode 1, buckling will occur in this way. Okay, so if you have a fixed end structure, this is your original structure, buckling will occur this way. Okay, so this is your deformation pattern. So from here, all the red are your deformation pattern. Okay, so mode 1 is the deflection that will usually occur first. If your structure is going to buckle, this is how it will look like first. Then now when N is equal to 2 is where we have mode 2 buckling. So in mode 2 buckling, what's happening? Okay, so again, we have a structure that's built in. Mode 2 buckling will look like this. Okay, so that is the now why is that? Is because the PL is the N. So if this expression is N pi, imagine if this is pi, 2 pi, 3 pi. If you plot it out, this is how you look like mathematically. Okay. And then for when N is equal to 3, is what we call mode 3. Okay. So mode 3 buckling, basically, so again, this is our structure that is built in. Mode 3 will look like this. Okay, so it goes across 1, 2, 3. So this is mode 3 buckling. Okay, so what I'm going to do now, I'm going to stop lecturing now. Now, those students, before I will stop recording first. Now, those